All right, so here is what I'd like to do. As I said, I'll give you a brief history of the problems that occurred in the 1992 Cricket World Cup, which led to the development of the DLS method. In particular, we'll talk about the reasons why that was a problem, and that was because the constructors of that method didn't think properly about how they were trying to model the metrics and the situation. So I said we'll talk about what's the proper way to do those sorts of things using proper data analytics, and then we'll talk a little bit about how those ideas can be applied generically to the concept of a rain rule, and we'll then have a little bit of a talk about other rain rules that have been proposed in as competitors. All right. So here is a little discussion of, as I said, a quick little history of the of what happened. Right. The method in place in the 1992 World Cup was a method which was called the most productive overs method. And its idea was that if the second team batting second had lost a certain number of overs, then what their new target should simply be whatever the team batting first achieved in the best equivalent number of overs. So if the team batting second had their overs reduced from down to 42, well, that means that they should have to outcompete the team batting first best 42 overs. Now, I think anyone who knows anything about cricket and has been thinking about these things for a little bit now will realize that that method works reasonably well for certain situations. It works, as says there on the slide, very well if the interruption happens in between the innings, which is quite common. But as we'll see, it has some very strong weaknesses if the interruptions occur at unfortunate times. And that's essentially the problem here, is that the framers of that method did not think holistically, and they were not data analysts who were setting it up at the time. They were essentially former cricketers who were trying to think about things from the perspective of the game and not from the perspective of dealing with models. And so, as you can see there, what happened was that England and South Africa were playing each other. England scored 252. And so initially, South Africa started off their innings needing 253 to win, but very close to the end of their innings, so there was a 45-over match at the time. They had reached 231, so they needed a further 22 runs to win, and they had just over 2 overs to do it in, and that's when the rain came. And as I said, that was a very unfortunate time for the rain to come, particularly using this method, because South Africa lost 2 overs, which meant that they needed to go back and look at, well, what were the best 43 overs that England had in their 45 overs of the first innings? And it just so happened that England had 2 maiden overs. There was one of those maidens had a leg bye, and that was the source of, you'll see if you go back to the first page, there's actually an error on that scoreboard there. It says 22 from one ball. In fact, the real target was 21, but that's somewhat irrelevant. 21 or 22 from a single ball is equally impossible. And then, so you can see where the issues are. I think that said that we took a game which was essentially poised reasonably evenly to a game that was essentially impossible, and it caused a huge consternation, as you might guess, and it led to a number of people thinking hard about this, and eventually, as I said, Frank Duckworth and Tony Lewis coming up with a better way, a more data analytics focused way of doing things. Right? So let's think a little bit about that. If we're going to consider this from a more holistic perspective, then there is no substitute in all of such situations for actually having data. We need data. All right. For those who are interested, I am now continually monitoring, well, not anymore since cricket isn't being played around the world for a while, but it will presumably come back at some point, right? And I monitor all that raw data, but as you might guess, there's lots and lots of it. And so the crucial aspect is, how can we look at it? How can we understand it so that we can really figure out a good way of coming up with a data analytics model. And this is, as I said, what Frank Duckworth and Tony Lewis did initially. Right? So here is the idea. Right? As I said, typically what we do is we look at the last 4 years. There is some debate about how far back you ought to go. I mean, cricket is an ever-evolving game like any sport. And so obviously information from 10 or 15 years ago is not relevant to the current play. On the other hand, you want to make sure that you have a wide enough window, that you have a big enough set of data that you can get some reliable results. So on that front, I've just sort of arbitrarily chosen a 4-year window. And obviously things fluctuate up and down, but as you can see up until recently, so this is based on my my last analysis, which was in July of last year. We have almost 250,000 pieces of information, which are essentially what occurred on every ball of every first innings of every international one-day cricket match, be it a 50-over match or a 20-over match. All right? But obviously, no human brain can compose 250,000 pieces of information and understand what's going on without proper visualizations. Right? So let me start by showing you how you shouldn't visualize and show you that it isn't just a trivial problem, and then we'll think a little bit harder about this. Right? So there is a graph of the number of runs scored on every ball of all of those 250,000 pieces of information. As you can see, there's not much that you can learn from that. Obviously, what you learn is that there are parallel lines there because you can't have fractions of a run on any given ball. You also learn that 0, 1, 2, 3, 4, and 6 are the most common values. For those of you who are concerned and understand cricket well, you may say, how did you get 16 runs on a single ball? Remember that this is runs per delivery, and that means that any illegal deliveries, a wide or a no ball, is counted as part of the previous ball. Right? So 16 runs on a ball is not 16 runs on one delivery of the ball. It's obviously composed there of a no ball or a number of wides. All right, but that graph is distinctly unilluminating, I would hasten to say. And so we might ask ourselves, how can we do better than this? Right, well, obviously one issue is that because the values on any given ball are whole numbers, a lot of the data points are sitting on top of one another. And so it's hard for us to tell in that row, those rows of zeros and ones and twos, well, how many actual data points are there? And that leads to a nice little idea that has been developed some time ago, given modern computing technology, the notion of what's called jittering. So in other words, you take a data point and you add a little bit of random noise to it so that you can see it better. Right? And certainly by doing that, we have enabled ourselves to see that a 3 and a 5 are far less likely. And in fact, even that 6 row is an interesting one because it shows you that 6s are far more likely towards the end of an innings than they are the beginning of an innings. But I think although this graph certainly isn't as bad as the first one, it really doesn't show us very much. And it doesn't show us anymore even if we start adding on little overall metrics. So here is the average runs scored on a ball. That does show you a little bit. It's steadily tailing up, right? The risks associated with scoring more runs on a ball are batsmen are more willing to take those towards the end of an innings because they no longer have to worry about surviving until the end of the innings and therefore maintaining their 10 wickets. In fact, wickets are a crucial aspect of that. So in fact, that red line is probably of no direct interest. We should probably split it up into averages per wicket. So there is a corresponding graph where each of the different colors now is the average number of runs conditional on how many wickets were available at the time. All right. But as I said, we still haven't really got anywhere where we can understand anything that's going on. And in particular, you can see that some of those purple and blue lines towards the early parts of the innings are wildly fluctuating because they're not based on a huge amount of reliable information. All right. Okay, so let's think a little bit about some principles of understanding data that we might use to help us with this. One thing is that, well, if really what we're after is those average lines, we shouldn't stick them down the bottom of the graph. So here is a picture where I've rescaled the vertical axis so that we get a better picture of what those averages look like. But I suppose that perhaps the fairest assessment of that picture is that it now is even clearer that it's meaningless, because it's just too fluctuating and too overlapped. Okay, so what we need to do is think more carefully, and this is what I say about the whole area of this section of the talk is on proper metrics. The whole area is on how do we actually measure what we really want to measure. And this was actually the major contribution, right? The single most important philosophical understanding that Duckworth and Lewis made. If you talk to Frank and Tony about it, they'll tell you that they did it while they were on vacation together in Hawaii. So there you go. If you are a data analytics person, maybe you get to travel a bit. And what they noticed was that although this graph is hard, if not impossible to comprehend, if we reorient ourselves so that on every ball we measure not how many runs were scored on that specific ball, but how many runs were scored from that ball forward to the end of the match, we get this picture. And so let me explain that picture as carefully as I can, because obviously it's the most important picture in the entire area. Each one of the dots on that graph represents the average number of runs scored from a particular point in the match forward. Right? So if you go to the horizontal axis to the number 40 there, that means there's 40 overs remaining in the match, and therefore the dots vertically above that point are, on average, the number of runs that would be scored from 40 all the way down to the end of the match. Right? And you can see that they tend to show us now some very obvious things. First of all, they show us the impact of losing wickets. So the red curve at the top is the score that you would get if you have no wickets down, so you have all of your wickets available to you. And as you lose wickets, obviously your potential to score runs decreases because A, you only have a limited number of wickets, and B, of course, the batsmen get, as we lose wickets, the batsmen that come in down the order are not as good as the batsmen at the top of the order. Right, and then finally, let me just point out that the different intensity of the points has to do with how many observations the average value is based on. So the ones that are the solid, very visible ones are based on at least 30 observations, and the rest are based, and the wild little squiggly spiderweb lines are based on less than that. So we tend to ignore those as simply saying, look, they're just too variable to be reliable. All right? And then because of that, you can see an interesting piece of the red curve, which is it starts out with some very heavy dots because all the one day, the 50 over matches start with all their wickets in hand. But eventually teams in that regard eventually lose wickets. You don't make it all the way through a 50 over innings without losing any wickets. And so then we start to get situations which are very rare. And then suddenly the graph gets dark again. That's because this graph is composed of both 50 over and 20 over matches. So where those red dots start to get bold again, that's where the 20 over matches start to come back in. And so those are the specifics. Right, and the other thing that we learn about this, which is perhaps the most important from our overall modeling perspective, is that we can have a look at, whoops, sorry, that wasn't what I meant to do. Go back a slide. Whoops. Apologies. Well, there's supposed to be another picture in there, which shows you that those graphs, I apologize for this, but these graphs here are curved. In other words, they're not straight lines. And that represents the fact that throughout the cricket innings, as we saw at least a little bit in the previous visualizations, even though they weren't so good, that there's acceleration, there is increasing scoring rates as we move through the overs. All right, so what does that help us do? Right? The actual DL methodology then works on this basic principle. It says, right, that if you translate those curves into proportion, so the average number of runs overall in a 50 over match is something like 260 or thereabouts. And so if we say, well, if you have all 10 wickets and all 50 overs, you're going to score 100% of your runs from that point on. That's obvious. we can then use that to also say, well, in any given situation, we can say what proportion of runs we would expect you to score. And so there's an example there. If the first team scored 249, so that team 2 are chasing 250 to win, and they've reached 150 for 4 in 35 overs, right? The question, and then Rain says, well, we're going to take the 10 overs away from you so that there's only 5 overs left for that team to bat out 40 available overs. The question is, what should the new target be? And the method says, well, if you have 15 overs remaining and 6 wickets available, then that graph would show you that you have just a touch under 40% of your score still to come. But if you only have 5 overs remaining and 6 wickets in hand, you only have 17.7% of your score to come. So in that sense, you've lost a little over 20% of your scoring potential. All right, so that means you should have to score 80% or thereabouts of what the first team did, and that's precisely what the DL methodology is. Right? So that's all it is. It says we have to come up with a way of determining what proportion of your scoring potential has been lost. And that's not simply a function of the proportion of overs that are lost. Notice that if I lose 5 overs from a 50-over match, 10 overs from a 50-over match, that's 20% of the overs, but in this case, I lost 21.7% of my scoring potential, and of course, it will be different in different areas. All right. Now, you may ask, what does DLS do? Well, DLS recognized that those proportions that we saw in that graph were are quite appropriate for average scoring matches, but what I was able to determine after I took over from Frank and Tony was that as the scores got higher and higher, as they are getting in the modern game, and when Frank and Tony were doing their analyses, the proportion of matches where the scores were above 300 was relatively small, whereas now a score of 300 is relatively common. In fact, scores of 400 happen even. And what I was able to notice was that, well, that acceleration, that degree of curvature that you find for matches where the score is 250 to 270 is not as pronounced as it is for matches where the score is much, much higher. Right? And so the DLS methodology says, we'll take those curves that we got from the DL approach, but as the score gets higher and higher, we damp them down. We make them slightly straighter so that the proportion of runs that are scored in the different areas of the match are changed a little bit. And so that's the concept of DLS. All right. Okay, so let's talk now a little bit about how we can use those metrics and those ideas to answer some questions about matches in general. So we'll use some data analytics to answer some key questions about cricket and the rain rule. And then, as I said, I'll talk a little bit about the principles involved in actually constructing a rule and trying to have it be responsive to a wider range of realistic situations as possible, so we can avoid the problems that were the cause of the disaster in 1992. All right, so here's one very, very common question. Why have I put the 50-over and the 20-over matches together? And in fact, most cricket watchers, I think, would agree with the statement that those are relatively different games, at least from a viewing perspective. All right? And I don't think anyone would disagree with that. However, from the point of view of data analytics, what matters is how similar they are from that analytical perspective. What do their scoring rates look like, so that we can decide whether a common approach to resetting targets is valid or not. So let me show you a picture here. Now, I haven't done this for all of the wickets just because I wanted the graph to be a little bit more less cluttered. So, but please be aware that if I had put wickets 0 through 9 on there as well, the picture I'm about to show you would stay the same. But I've just picked out 2 of them. So these curves are exactly the curves that I showed you on that very first rainbow graph, with one small difference. These are now the curves for 1 wicket and 5 wicket for only the 50-over matches. And so those are the one-day international scoring curves with 1 wicket down or with 5 wickets down. And what I'm about to do when I hit the bar next is I'm about to overlay exactly those wicket packages or those wicket values for the 20 over matches. All right. Now, obviously, that overlay won't have anything for the horizontal axis between 50 and down to 20, since 20 over matches only have at most 20 overs in them. All right. But what you'll see is that they fall exactly on top of the one-day matches. So the scoring rates, when we adjust for the wickets down, are identical. And if we are using simply these curves as our basis for understanding how to adjust scores, then we certainly don't need a separate method for the 50 versus the 20 over game. Right? You may ask, well, then why does it seem that the 50 over and the 20 over matches are so different? And the answer to that is essentially the break in that red curve, if you think back. Right? Essentially, the problem is that in a 50 over match, we almost never reach 20 overs to go with all 10 wickets in hand. So even though in principle we're saying the last 20 overs of a 50 over match is the same as a 20 over match, right? We are not in, right? We see situations in the actual 20 over match which are not commonly observed in the 50 over match. But theoretically they're there, and that is the point. Right? That if we want to come up with a methodology, we have to think holistically about this rather than about just the specific matches that we have in our heads as being the common exemplars of what can or can't happen. Right? So, right. Just to continue the point, here's another question I get asked all the time, and that is, right, why do you use the same methodology for both men's and women's matches? Aren't they notably different from one another? Right? The answer, of course, is, well, they are different from one another, and here is a picture, again, of men's versus women's matches. Again, I've only picked the 2 wickets down curves, excuse me, for the sake of making the graph viewable. And if you look at it in terms of actual runs, you'll see, as you would expect, that the men's curve is much higher than the women's curve because men score more runs on average. They hit the ball farther, they score more sixes and more boundaries. Right? But again, we're not interested in actual runs. We're looking at scoring percentages or proportions, scoring potential. And so if we take those curves and we divide each of them by the total number of average runs in each of those matches, right? So I said for men it's about 260, for women it's about 220 or so, and rising rapidly. The women are getting better at scoring. And if we do that, right, so we adjust these into percentages, you again see that they fall exactly on top of one another. So while the games are certainly different from an absolute perspective, from the point of view of run scoring patterns and run scoring potential, they are essentially identical. Right? So there's no need for an additional method to distinguish between the men's and the women's game. Now, as I said, I do annually, we reanalyze data. The women's game is making giant strides forward since the vast majority of the women players in the world have become fully professional, and so their scores are rising. And so we keep an eye on this, and it is not inconceivable that in the future there may actually need to be separate approaches for men and women. But at the moment, their scoring patterns in a percentage scenario are sufficiently identical that there really is no need. Okay, so let me just then enter into the final phase of what I want to talk about and what I really want to focus on, which is the concept of how to really appropriately apply analytics and to think about these things. As I said, the thing which caused the problem in South Africa was that the rule that was in place was designed by people who thought about, well, what is the most common scenario, and let's figure out an idea to fix that, rather than thinking about general principles about what should a rain rule do and how can I devise a methodology which satisfies those principles. So in my view, and look, there are other potential views in the world there, but my view is that there are 5 key principles which any rain rule should satisfy to so that it satisfies common sense, but also it, as we'll see in just a second, it essentially keeps the character of a cricket match. There are certain things about cricket, as you'll see. One of them, for example, is that it doesn't matter how you score your runs, it just matters, or when you score your runs, it just matters how many. Right? So in other words, if you score more than runs in a game than your opponent, you win. It doesn't matter whether you scored all those runs at the very end of your innings or all of those runs at the very beginning of your innings. No, it just matters the total number. Right? So that's a principle that we'll want to maintain. Right? Right. Another set of obvious principles, and every rain rule I've ever seen proposed obviously satisfies these, because if it doesn't make any sense, and that is these are so-called monotonicity principles. It basically says that, and so I've tried to write out the rules in pure math language for those of you who are interested in that sort of thing, but I'm going to talk in terms of the little orange, more human language, if you will. The idea behind the two monotonicity principles is that it should never be a disadvantage for a batting team to score more runs. That's their goal, is to score as many runs as possible. So if the rain rule says you would have had a better target or a better scenario for yourselves if you'd scored fewer runs, then that's clearly a problem. And the same is true from the bowling perspective. It should never be a disadvantage for the bowling team to take more wickets. All right? So those are fundamental principles. All of the common rain rules that have been proposed have those features. Some of the rain rules that have been proposed don't even take account of wickets at all, so it's not an advantage or a disadvantage to take wickets in those situations, but at least it's not a disadvantage for them. All right, and today I'll be comparing three general types. So I said obviously DLS, my own construction, and the two most common or most famous potential competitors, VJD, which was developed by an Indian engineer, and the Wasp system, which was developed by a couple of New Zealand data analysts. All right, so let's think a little bit about the rest of the other principles. Depending on how you count, there are either 2 or 3 of them, and here they are from my perspective. So, right, the idea is that, right, the third principle is, as I was saying, when you score runs, shouldn't matter. So if I score 250 runs, and I score 200 before the break and 50 after the break, I should have the same result, be it a win, a draw, or a loss, as if I'd scored 150 before the break and 100 after the break, and total 250. Right? So, assuming that the break was in the same place. Right? So if the innings is interrupted in exactly the same way, then it shouldn't matter whether you score before or after the break. All right? And then lastly, the final principle, and the reason it's subdivided, is that both of these principles are based on a very important concept, the concept of a par score. And I said, rather than go into the mathematical details, let me just give you the general notion of a par score. All methods that are created have a par score, because its idea is it's the score which, if the match was stopped at that point, it would have to be declared a draw. And so there will always be a point at which a match, if it's terminated, assuming that enough overs have been played so that the match is declared a valid match, someone has to be declared the winner unless the game was at par. All right, and so here is a fundamental principle. It basically says, look, if you are at par when an interruption occurs and the game is able to be resumed at some point in the future, when the teams come back on, they should be at par still. In other words, a game that's evenly poised should remain evenly poised before and after a break. That seems perfectly reasonable. All right? And then the last bit based on that is essentially saying that, well, the par score is essentially saying what is the average number of runs that are likely to have been scored in the piece of the game that was missing, because that's how we decide. So I said, well, if a team loses a particular piece, we'll figure out what we expect, what percentage of score they should have gotten there. That would be the par score associated with that missing piece, and that would be the piece we would subtract from their target. Right? And so what we're saying here is that, well, that par score, right, associated with a piece of an innings should not depend on whether that piece was missing or not. In other words, right, just because rain came and said these 10 overs are not being played, that doesn't mean that if those overs had been played, we would have expected a certain score in them. Those two things should be the same. That's the idea of the rain rule. It says, what do we think on average you would have scored? Well, if we think that you would on average score something different if you didn't participate in the overs as if you did, well, that's not really following the principle that we're after here. Right, so those are the generic principles. And hopefully, the idea behind them is simply to preserve some obvious notions about what a cricket match is and about who the winner of a cricket match should be. And then from there, we'll develop a methodology which or ensure that our methodology satisfies those. And if we do that, hopefully, if our principles are broad enough and correct enough, we won't be able to develop a method like the most productive overs method, which leads to disastrous results in certain situations. All right, so let's see what happens. All right, I just want to go over some interesting consequences. One of the most common questions that I get asked is, why don't we simply reset the target so that the probability of each team winning remains the same? And you'll notice that we do that in one very specific scenario. In other words, if there's a 50-50 situation, if we're at par, then we guarantee that when we come back, we're still 50-50. But we can't possibly do that in situations where one team is ahead. In other words, if one team is ahead of par, then we have to say that that team has an advantage, because eventually, if the game is washed out from that point forward, they will be declared the winner. So there's no way of actually maintaining probabilities exactly in that sense. Eventually, one team will have to be given a 100% chance of winning if the rain stays long enough. Right? Moreover, it's very common in sport, right, this notion that, well, the team that's ahead wants the game to be shortened. If you watch any sport in the world, right, if you watch a football match, the team that's ahead, when there's only 3 or 4 minutes left, what do? They dribble the ball into the corner flag and they try and waste time. Right? Conversely, if you were watching a basketball game, the team that's behind in the basketball game incessantly fouls the other team to try and extend the length of the game, because fouling stops the internal clock from running. Right? So the team that's ahead wants a shortening. So there isn't any problem with the notion, at least in my opinion, that the team that's ahead in a cricket match is getting a slight advantage the shorter the game is made, because they have to maintain their lead for less time. Or conversely, the team that's behind has less time to catch up. All right. So let's see how that plays itself out. You can argue, so well, all right, you wish to argue with me. Let's see what the consequences are of a probability preserving method. And one of the most common of those is this method called Wasp, but it's not the only one. And so here's the basic idea. Right? Suppose that we are looking at 3 different matches, but they're all very similar, right? So in each of the 3 matches, the team is chasing a particular score to win, and at a certain number of overs, the matches are interrupted by rain. The only difference being that in the first match, the team that's chasing is a little bit ahead of par. In the second match, the team that's chasing is exactly at par. And in the third match, the team that's chasing is a little bit behind par. All right? So, by definition, the team in the middle is on 50-50, whereas the teams at the either ends are either a little bit more than 50 or a little bit less than 50% chance of winning in their chase. All right. So obviously, the middle match, right? We say, well, in order to preserve our principle number 3, they should come back at par. And so their total target to win should just be whatever they scored that was par in their first section, plus whatever the curves that we've got show the par score to be in their overs that they get remaining once the interruption is over. Right? So they should have par 1 for the first section, plus par 2 for the second section, plus an additional run. Obviously, to win, they have to get 1 more than the par score. All right, but what you find is that if you use that same par score in the other 2 matches, you increase or decrease the probability of winning, right? It's easier for the team in match number 1 to score par 1 plus par 2 plus 1 because they're already a little ahead of par. So they now have a slightly increased chance of winning from their chance, right? They were a little bit more than 50 to start with. They're now much larger than 50. Well, perhaps not much larger than 50, but certainly more than that 50. And conversely, the team that was behind is now a little further behind. All right, so if we are to rearrange this so that we maintain the probabilities, what we need to do is we need to say, well, no, the target for the team batting first needs to be a little bit more. In other words, if we just kept their par score to the same par as the team in the middle, they have an increased chance of winning. If you want to maintain their probability, then they need to have a target which is a little bit bigger. Notice that, interestingly, that what's happening there, and this is one of Frank and Tony's great insights on this matter when we discussed it, is that what you're essentially doing there is saying that the target has to be bigger for the team in match one because they've played better, which seems a little bit unfair, right? If they're playing better, why do they have to have, why do they need a higher target? And conversely, the team that was a little behind, they get the benefit by having their target reduced a little bit. And you can then see the anomaly that can arise from this by saying, well, suppose that when all three teams come back, right, the first team comes back and they don't play as well as they did prior to the break, so they score exactly X less than the par of the remaining piece, so their overall score at the end of their innings is precisely the par score. And similarly, right, the team in the middle scores exactly the par score, and the team at the end comes back and plays slightly better than they did before the break. They score the par score plus an additional amount. And what we've got there now is three matches, each with identical breaks, each with identical innings structure, and each with an identical final score, but with three different results. All right? In other words, the team in the first case scored the par number of runs, but because they scored more of them before the break than after the break, they're deemed to have lost. Whereas the team in the third scenario has scored the par number of runs, but because they scored more of them after the break, they're deemed to have won. Now, all right, in my mind, and I hope in most sensible cricket players' minds, that's not acceptable. The point of, I said, one of the defining features of a cricket match is that it doesn't matter when you score the runs. All that matters is the combined total of them at the end of the innings. Right? So this is an example of how, if we are to envision a probability-preserving approach to our target setting, and we don't think about it holistically, we will wind up creating an approach which has a notable anomaly in it. And this is what happened in 1992. They just didn't think broadly enough. And so probability-preserving ideas certainly sound good, but they lead to an approach which is not cricket, if you will. All right. All right, and then we'll just lastly talk a little bit about the other most common competitor for the DLS method, the VJD method. So the VJD method is not a method based on probabilities either, so it does not suffer from the problem I've just mentioned. However, it does suffer from a problem associated with the final principle, which is to say, right, we shouldn't have parts of our innings which are different depending on whether we play them or whether we have them cut. And so let me just give you an example of that. Right? So imagine we play a match which, after 30 overs, right, a team chasing a target of 250, after 30 overs, that both teams are exactly at par. This is based on the VJD software, which is available on his website. And so there are 115 runs for 2 wickets down, which turns out to be VJD par. All right, and now imagine two different versions of the match from that point on. In the first one, the team just keeps playing. All right, so after another 10 overs, if they are at 170 for 2 now, they would remain at par, according to the VJD software. And that means that in order to win, they need to score 81 runs in those last 10 overs. All right, alternatively, if the 10 overs that between 30 and 40 are lost, well, then our guiding principle, which says that you come back, that if you were at par to start with, then you come back at par as well, means that technically that team is still at par, and therefore whatever they need to score to match the VJD target is what VJD feels is par for those last 10 overs. And his software indicates that the target in that situation should be 204. And in other words, he's saying that that team needs to score 89 runs, right? Or perhaps more explicitly, what he's saying is that in the 10 overs between 30 and 40, if the team actually plays those overs, then they're worth 55 runs. But if those overs are lost, they're worth only 47. Right? Now, that is, in my, again, opinion, not an acceptable aspect of a basic range setting rule. Right? There is a reason for it. Right? Right? There is a mathematical structure for those who are interested in it inside the VJD method, which is called the target curve. And it essentially reshifts things. That target curve is only in use when the matches are shortened. So if you wish to get par scores without shortening, you get a different calculation than if you get par scores with shortening. And because of that, the VJD method is not in compliance with this fourth and or fifth principle. All right, so that is basically where we're at. I said the ideas here, let me just recap a little bit. The idea was, first of all, in order to get a good sense of any appropriate modeling situation, you need proper visualizations. You need to think about what is it about this data that is giving me the fundamental important view, right? And there are many, many possible visualizations of a large set of data. Some of them will be useful and others of them will not. And hopefully the useful ones will give you guidance as to, well, what is the actual metric? As I said, in this case, right? The obvious metric of, well, let's just look at the number of runs scored on each ball is not a useful metric because it's just too variable, right, and too specific. Instead, if we look at the total number of runs to come, what we get is a more stable and more understandable and more modelable, if you will, structure of that information. And then the second point was, well, we need to make sure that once we've understood the structure, that we come up with a way of modeling what we want to do, which is not based on a long series of, let's look at this match, let's look at that match. As I said, for those of you who have potentially followed the conversation between myself and Mr. Jayadevan, who's the one who's constructed the VJD method, he likes to point out individual matches where he feels that his approach is given a better result. But as I said, if one focuses solely on a long list of individual matches, I believe one misses the point of what's actually important in a data analytics exercise, which is, as I said, the holistic approach. We need principles that we should satisfy, not I need to make sure that this match it works well in all the situations I can think of as having happened. Right? Because otherwise, you will inevitably wind up with a situation which didn't happen in your thinking and will cause a 1992 semifinal disaster to occur.